In this video, we are going to talk about exponential growth and decay. So we're continuing our section on separable differential equations. So let's start with an example, which says on January 1st, 2006, the world population was 6.51 times 10 to the 9, which is about 6.51 billion. Each year, the number of babies born is 2% of the population, and 0.84% of the population dies. According to this model, what is the population now? So the first thing I want to remark is when we have a word problem like this, I want to begin by defining my variables. So I'll be able to convert this into an equation, something I can work with. So the problem talks about the population. So let's have a variable to denote that. I'm going to let that be P of T. So that's going to be the population T years after that starting point, which is after January 1st, 2006. And we're also told a specific piece of info about what the population is at that moment in time. So that would be the population at the 0 year mark. So that would be P of 0, and that is 6.51 times 10 to the 9. All right, so we are given this. We're also told something about, how many babies are born each year and then how many people die. So that's telling me how much the population is changing. So the change in the population equals, well, it's the number of births minus the number of deaths. When we subtract those two things, that's determining how much the population is changing. So the change in population, that rate of change, that's a derivative. So that would be, and the population, the variable for population is P here. So this would be dP dt, the rate at which the population changes with respect to time. And for the number of births, the problem tells me, well, each year it's 2% of whatever the population was. So 2% as a decimal is 0.02 of means multiply. So that's going to get multiplied by the population, which we're calling P. So 0.02 times P. All right, and then I got minus the number of deaths. And the problem tells me that, well, that's 0.84% of the population. So if I convert this to a decimal, we get 0.0084, right? Because I moved the decimal 2 spots to the left. When I do that, I have to add an extra 0, so 0.0084. All right, so I multiply this by the population, which is P. Okay, so if I subtract these, this simplifies to 0.0116 P. So now I have this differential equation, and let's separate variables. So I can take this P, I can divide it over here to get it with the dP, and I can take this dt and multiply it over to the right. So that'll give me dP over P on the left equals 0.0116 dt on the right. Now I can take the integral of both sides, now that the variables are separated. So on the left, that antiderivative is natural log absolute value of P. On the right, I'll get 0.0116 t. And we've seen before that when I do this integral on both sides, I got to put a plus c on one of those sides. So I'll put a plus c here. I'm trying to figure out what the population is. So I'm trying to isolate the p eventually. One thing I notice is it's inside of an absolute value, but there's something I can make use of to simplify that. So P in this problem is a population, and the population is gonna be, it can't be negative. It's gonna be greater than or equal to 0. As a result, this implies that the absolute value of P, well, if P is not negative, I can just drop the absolute value. It's the same thing as P. Okay, so nice. So instead of writing absolute value of P, I'll be able to just write P going forward. So to isolate the p now, I can transform this log equation to exponential form. Remember, the base of ln is e. So when I transform it, I get e to this whole thing power, e to the 0.0116t plus c equals this thing, absolute value of p, which I know is just p on the other side. I could also have gotten that by just doing e as the base on both sides. Then the e and the ln would have canceled to give me p on one side. And on the other side, I would have gotten this, which is what I have. So that's another way I could have gotten there. All right, so we have this. I can simplify this a little bit. So I can simplify this. I can use an exponent property on this e term, because that becomes e to the 0.0116t times e to the c. And then what I want to notice about this is e and c are both just constants. So this whole thing I've circled as a constant. I can just rename it and call it k. I can call that thing k. So I now need to solve for k. So let's solve for k. For that constant, this is where we use this initial condition. So if I use the fact that I know p of 0, if I plug in 0 into my equation for p, we'll get e to the 0 times k. And that should be equal to 6.51 times 10 to the 9. So e to the 0 is just 1. So this gives me that k equals 6.51 times 10 to the 9. All right, so I have the value of k. I'm ready to take that and plug it into my equation here for p. So my equation for p, and let me just go ahead and rename it as p of t, because p is a function of t, is going to be, so k is 6.51 times 10 to the 9, and that should get multiplied by this other e term, so by e to the 0.0116t. All right, so that is my formula for p of t. What is the problem asking? What is the population now at this moment in time? So now, at least in the moment when I'm making this video, the year is 2025. So that is 19 years after 2006, which means I'm using t equals 19, and I plug that in to this equation. So if I plug in 19, so if I do p of 19, and I work out what this is, I'm going to go ahead and use a calculator to work this out. This is about 8.11 times 10 to the 9. So about 8.11 billion people, at least according to this model. Okay. So this many people. All right, and there we have it. Okay, so let us give a definition now. When we have a population or some quantity that is growing at a rate that's proportional to its size, our differential equation will have the form, so the derivative of p, so p prime of t, should be equal to, when I say it's proportional to its size, it means it should be equal to, p of t, the size, but multiplied by some constant of proportionality, which I'll just call k. And that's what we were seeing here. Our derivative was equal to p just multiplied by some constant. When it has that form, that corresponds to some type of exponential either growth, or it could be exponential decay. As we saw here, when we solve the equation, that'll end up having the form p of t equals, there'll be some constant in front, which I'm just going to call that y naught, and then times something like this. It'll be e to the k times t, because notice the same value, this constant I had in front, was here in the exponent, and that's not a coincidence. All right, where y naught, this constant that's in front, well, the constant in front, notice that was just this initial value. So y naught is what I get if you plug in 0 into your function for P of t. And K is called the growth or decay rate. And that depends on if it's positive, then it's a growth rate, or if it's negative, and then it's a decay rate, it's shrinking. So when I have a function of this form, it's called an exponential model, right? This is an exponential function. All right, so follow up to this problem. Now, how long would it take to double 2006's population, assuming the same rate of growth? So if I want to double that population, what I want to do is I need this population to be 2 times what we started with, 2 times this value. So let's let P of t equal 2 times, so 2 times that starting amount, which was 6.51 times 10 to the 9, and maybe I'll put a parentheses around this to really exaggerate that it's 2 times that initial amount. So if we plug that into this equation, so the left on P of t, we're plugging in 2 times 6.51 times 10 to the 9. That'll be equal to the right side, which is 6.51 times 10 to the 9 times that e to the 0.0116t. So I can divide both sides by this 6.51 times 10 to the 9, and that'll leave me with a 1 in both of those spots. So I now have 2 equals e to the 0.0116t, and I have to solve this equation. So I can do that by transforming this to a log. So when I do that, e, if this base is e, I have to use log base e, which is ln, and I'll get ln of 2 equals this exponent, equals 0.0116t. So the other way I could have seen that is if I did ln of both sides, so ln of this side and ln of this side. On the right-hand side, the ln and the e, they kind of cancel, and you'll just get that 0.0116t. And on the other side, I have ln of 2. All right, so I have this. Now to isolate t, I divide, and I get t equals ln of 2 divided by 0.0116. All right, so if I wasn't allowed to use a calculator, I could leave it like this for my answer. But if I do have the luxury of a calculator, I can plug this into one, and I'm going to round it to a whole number. This is about 60, and the units of time in this problem are years. So at this growth rate, it would take about 60 years for the population to double the value of what it was at 2006. All right, so now let's talk about a situation involving exponential decay. And the example I want to look at is talking about radioactive isotopes of elements. So carbon-14 is what's called a radioactive isotope. So radioactive substances are unstable, and they tend to split into smaller particles that are more stable over time. So they tend to split and divide over time. While some radioactive elements are quite harmful, carbon-14 typically occurs in such small quantities that it is safe. Like all radioactive elements, it decays over time, and we can measure its rate of decay using what's called its half-life. So what does half-life mean? Half-life is the amount of time it takes for, I'm going to fill in the blank, half of it to decay. And carbon-14's half-life is 5,730 years. So what that means is, let's say I started off with like 40 grams of carbon-14. Well, after 5,730 years, I would be left with half of it. I'd have 20 grams left. After another 5,730 years, I'd have half of that, which is 10 grams. And I'd continue forever like this. After another 5,730 years, I'd cut that in half, and so on. So one of the things that carbon-14 is used for is determining how old objects are, such as fossils. So let's end with an example. All right, so the example says that carbon-14 decays at a rate that's proportional to the amount that is present. An animal's bone had 1,000 grams of carbon-14 when it died, and now the bone has 100 grams of carbon-14. How old is the bone? All right, so the first step when I have a word problem is to define variables. So the problem talks about like the amount of carbon-14. Let's define a variable for that. So for amount, maybe I'll call that A, capital A, changing over time, so it should be a function of t. So this will be the amount of carbon-14, which in this problem is measured in grams. In grams, and let's have it be t years after the death of the animal. All right. So one thing I want to notice about this that'll speed up the problem for me is it tells me that this is decaying at a rate that's proportional to the amount present. Well, that's exactly the setup that it says for an exponential model. It's either growing or decaying at a rate proportional to its size, however much there currently is. So I'm going to use that fact to go straight to the equation without having to do the differential equation and antiderivative. So I can use this fact to say, oh, it's exponential. It is exponential. And what the previous page says is, well then, sorry, that should be exponential, and then I'll put my exclamation point. The previous page says, okay, my function for a of t should have this form, y naught times e to the kt. So that'll be y naught e to the kt. It'll have that form. And I know y naught should represent the initial amount. So y naught for this problem is 1,000 grams. So I'll just write the 1,000 right now without units. I'll write down the units at the end. Okay, but I still need to find k. So let's find k. And to do that, I can take advantage of the half-life. We know that after 5,730 years, that instead of there being 1,000 grams, I'll just have half of that. I'll have 500. So I know that if I plug in 5,730 in for the t, so if I do that, I get, so y naught is 1,000, and I get e to the k times 5,730. So if I plug in 5,730 for t, I should end up getting just half of this initial amount. So I should get 500. Okay, so I should end up getting this. So if I simplify this now, if we simplify this, so let me just make a note of this. This is half. Oops, sorry. Half of what we started with. All right, so I can divide the 1,000 over. So that gives me e to the 5,730k equals, if I divide 1,000, I'm left with 1/2 there. And now I can convert this to log form. And if I do that, I'll get ln of 1/2 equals this exponent, 5,730k. And isolating for k, what I'll get is that k equals ln of 1/2 all over 5,730. Okay. Now, there's one simplification I'm going to make to this, which I don't have to do, but I think it helps to illustrate something that's going on, so I'll do it, which is this k, if it's positive, that indicates that the quantity is growing. And if it's negative, that indicates it's decaying. The problem is saying that the amount of carbon-14 is decaying. It's because it's radioactive. It's shrinking over time. So, well, it doesn't look like this is negative, but it actually is. So there's one thing I can do, which is 1/2 is the same thing as 2 to the negative 1. And I can use one of my log properties to move the exponent in front of the log. So that'll be that negative in front, and then ln of 2 all over 5,730. And now it's more clear that, oh yeah, this is negative. There was a hidden negative here. All right, so I have the value of K, but let's answer the question now. When is this bone going to have 100 grams of just carbon-14? So when are we down to just 100 grams? So to answer that, I got to plug in 100 in for this A of t, for the amount. So I'll have 100 equals, y naught is 1,000. And then I get e to the, and then k is negative ln of 2 over 5,730 times t. I can divide the 1,000. That'll give me 1 over 10 equals e to the negative ln of 2 over 5,730 times t. Now, from here, I can convert this to log form. So doing that, I'll get ln of 1 over 10 equals the exponent of this. So that'll equal negative ln of 2 over 5,730 times t. And then to isolate the t, we take this whole fraction and I'll divide it over. We'll divide it over here. Or that's the equivalent of, yeah, so let me just go ahead and divide it over. So let me just separate this. I'll get t equals ln of 1 over 10, all divided by negative, or actually, sorry, instead of dividing by this, let's just multiply by its reciprocal. I think that just looks a little nicer. So I got this multiplied by its reciprocal, so negative 5,730 over ln of 2. So if I didn't have a calculator, I could leave my answer like this. But if I use one, I get that this is approximately, if I round to the nearest year, it's 19,035 years. And I have an estimate. I have an estimate for how old this fossil is.